Have you ever gazed upon the night sky and pondered the infinite expanse of the cosmos? A realm filled with secrets, mysteries, and wonders beyond our comprehension. It's an unfathomable expanse that stretches out past our humble planet, past our shining sun, past even the most distant galaxies we can perceive. Its vastness is so immense that it boggles our minds, dwarfing our grandest imaginations. And within this vast cosmic arena, there exists a multitude of mysteries that baffle even the brightest minds of our time. These are not mere riddles to be solved, but profound enigmas that challenge our understanding of reality itself. They are the cosmic conundrums that keep astrophysicists up at night, the perplexing puzzles that beckon us to delve deeper, to probe further into the cosmic abyss. So brace yourself as we journey into the enigmatic cosmos, unearthing its disturbing secrets one by one. Imagine a time when the universe was nothing but a dark, silent abyss. This was the cosmic Dark Ages. In the aftermath of the Big Bang, the universe plunged into a time of profound silence and obscurity, a period we now refer to as the Cosmic Dark Ages. This epoch lasted for hundreds of millions of years, a time when the cosmos was an all-encompassing void, devoid of any light or sound. Picture the universe as an infant, having just been born, yet shrouded in a blanket of darkness. There were no stars, no galaxies, no radiant bodies to pierce the universal gloom. All that existed were sparse particles of matter and dark matter, lazily drifting through the cosmic sea, seemingly aimless and random. But then, something remarkable happened. As the universe cooled and expanded, these particles began to coalesce, forming the first atoms, primarily hydrogen and helium. Over time, these atoms clustered together, growing denser and denser until they collapsed under their own gravity, sparking the nuclear reactions that birthed the first stars and galaxies. This monumental event marked the end of the cosmic Dark Ages. These first celestial bodies, with their intense heat and light, started to illuminate the universe, filling it with radiance and life. The mysteries surrounding this period are still being unraveled. And so, from the inky blackness, the first celestial bodies were born, piercing the universal darkness with their light. We now leap forward to a gravitational anomaly that has been baffling scientists for decades, the Great Attractor. In the vast and wondrous expanse of our cosmos, there's something rather peculiar happening. Imagine a colossal unseen force, tugging not only at our Milky Way, but also hundreds of thousands of other galaxies, dragging us all towards one common direction. This is the Great Attractor, a gravitational anomaly in the heart of the Laniakea supercluster, our cosmic address. But what exactly is this Great Attractor? Well, that's where things get a bit tricky. You see, it's hidden from us by the zone of avoidance, an area of the sky obscured by our own Milky Way. Our galaxy's dust, stars, and interstellar gas form a cosmic veil, shielding us from directly observing what's pulling us in. Scientists propose that it could be an immense concentration of mass, approximately 10,000 times that of our Milky Way. However, the true nature of this celestial enigma is still largely unknown. Its gravitational pull is so immense that it's dragging us towards it at a staggering speed of over 600 kilometers per second. Yet despite our relentless pursuit of knowledge, the Great Attractor remains elusive. It's a cosmic riddle, a testament to the vastness and complexity of our universe. We're caught in its gravitational dance, yet we can only speculate about what's leading the tune. As we hurtle towards this enigmatic entity, its true nature remains shrouded in cosmic mystery. To the unseen forces that govern the cosmos, dark matter and dark energy. The cosmos is filled with an aura of mystery, and at the center of this enigma are two invisible entities, dark matter and dark energy. Together, they make up a staggering 95% of the universe, yet they remain largely undetected and unexplained, cloaked in a thick veil of darkness. Beginning with dark matter, it is a form of matter that doesn't interact with light, making it invisible to our current scientific instruments. But how do we know it exists, you might ask? Its presence is detected indirectly through its gravitational effects on visible matter, such as the spinning motion of galaxies. Without the gravitational pull of dark matter, galaxies would simply fly apart. On the other hand, dark energy is an even more mysterious entity. It's a hypothetical form of energy that permeates all of space and accelerates the expansion of the universe. It's like an unseen hand, constantly pushing the universe to grow larger and larger. The existence of dark energy is inferred from the observation that the universe isn't just expanding, but doing so at an accelerating rate. The nature of these two invisible entities is one of the greatest unsolved puzzles in cosmology. Despite their elusiveness, they are integral to our understanding of the universe. They influence the formation and evolution of galaxies, the expansion rate of the universe, and potentially even the fate of the cosmos itself. Yet, we still know so little about them. What are they made of? How do they interact with visible matter? Why is there so much more dark matter and dark energy than regular matter and energy? These are questions that astrophysicists are racing to answer. These unseen forces, although invisible and mysterious, are the cosmic glue holding our universe together. We may not fully understand them yet, but their existence reminds us of how much more there is to learn about our fascinating universe. Have you ever wondered if we are alone in the universe? This brings us to the Fermi paradox. With an estimated 2 trillion galaxies in the observable universe, each potentially brimming with billions of stars, the likelihood of Earth being the sole cradle of life appears infinitesimally small. Yet, we've found no evidence to suggest otherwise. This conundrum is what we call the Fermi paradox, named after the physicist Enrico Fermi. The paradox poses a simple question. If there are a multitude of technologically advanced civilizations in the universe, why haven't we detected any signs of them? It's a question that continues to perplex scientists and stargazers alike. The Fermi paradox is not a statement of fact, but a collection of questions that challenge our understanding of the universe. It forces us to consider the vastness of space and time, the nature of life and intelligence, and the many barriers that could prevent civilizations from contacting one another. Some speculate that intelligent life is a rarity, perhaps even unique to Earth. Others propose that advanced civilizations might be avoiding us, or that we simply lack the means to detect their signals. The universe, after all, is a big place, and our technology is still in its infancy. There are also darker theories. Some suggest that civilizations inevitably self-destruct before they can reach out to the stars. Others propose the existence of a great filter, a sort of cosmic roadblock that prevents life from spreading beyond its home planet. And then there's the possibility that we're just not listening correctly. Maybe we're like ants trying to understand the internet, oblivious to the cosmic web of communication happening right above our heads. Despite the numerous theories, the Fermi paradox remains unsolved. It's a cosmic riddle that highlights our thirst for knowledge and our longing to be part of a larger galactic community. As we gaze upon the stars, the silence of the cosmos continues to puzzle us. Every story has an end. But what about the universe? Will it too meet its demise? The cosmos, this vast expanse of everything we know, might seem eternal, but even it has its theories of an eventual end. Let's delve into some of the most intriguing possibilities. First, consider the Big Rip. This theory suggests that the universe's expansion, driven by a mysterious force known as dark energy, could accelerate to such an extent that it literally rips apart all matter, from galaxies and stars to atoms and subatomic particles. Imagine, if you will, the fabric of space-time itself being torn asunder, leaving behind, well, nothing. Then there's the Big Crunch, the polar opposite of the Big Rip. This theory posits that the universe's expansion could slow down and eventually reverse. The galaxies would start to move closer, converging into a singular point of infinite density, a mirror image of the Big Bang. Essentially, the universe would collapse in on itself, a cosmic implosion of unimaginable magnitude. Lastly, we have the theory of heat death, or the Big Freeze. This is a more passive end, where the universe continues to expand, but at a decreasing rate. Over trillions of years, stars would burn out, galaxies would drift apart, and all matter would eventually decay. The universe would become a cold, dark, and lifeless place, with its energy evenly spread out, leaving no room for life, light, or motion. These theories, as chilling as they may sound, are mere hypotheses based on our current understanding of physics. The truth is, we don't really know what the end of the universe will look like or when it will occur. Will it be a violent cataclysm, a slow decay, or something entirely beyond our comprehension? As we stand on the brink of cosmic understanding, the ultimate fate of our universe remains a haunting uncertainty.